lecture 11. Yesterday we were talking about the maximum swing permissible in order to make sure that the output of the amplifier is not clipped. And what did we see? We saw that when you plot the locus of the drain potential in the ID VDS plane, we were, let's say, biased at some quiescent operating point VDS1 and some quiescent current ID1, and the limit of the saturation region is some kind of parabola like this, and the locus of VD as the input signal Vs goes on varying has to be a straight line. Why? Because the incremental voltage Vd is given by minus Gm times RL parallel RL1 times Vs, and the incremental ID is given by Gm times Vs. So you can think two separate equations being dependent on a single parameter Vs. So clearly the change in the drain current, that is, which is the small ID, is related to the change in the drain source voltage, which is the small Vd, by a straight line. And what is the slope? Minus 1 over RL parallel RL1. So you get some kind of straight line like this. When the straight line intersects the x-axis, the transistor goes into, the transistor is cut off, okay, and when this line intersects this violet curve, okay, this is the point at which the transistor M1 enters the triode B. And once the transistor enters the triode region, what happens to the incremental gain? The incremental gain reduces, okay, which basically means that if the input was a sine wave, you can think of the output gain reducing suddenly when the input goes above a certain value, okay, which basically I showed you intuitively that it will basically cause clipping of the sine wave. Similarly, when the transistor is cut off, there is no drain current at all, so any change in the gate source voltage does not affect the output voltage, and the top half of the sine wave gets clipped. So these are the two catastrophic effects on the sine wave. The lower part gets clipped off when the device goes into the triode region. The upper part gets chopped off when the transistor goes into the cutoff phase. So let me just take a quick example so that we drive home the point. So let me say this was 2.7 volts, this was 2 meg, this is 700K, mu n Cox of the transistor was, what are the units of mu n Cox? Amperes per volt square, and typically in microelectronics work we don't deal with amperes of current, we always deal mostly with microamperes of current. So it makes sense to usually express this in, rather than amps per volt square, it makes sense to express it in microamperes per volt square. And let's say the W by L of the MOSFET was 25. Let's say this load resistance was 10 kilo ohms. The source had an output impedance of 1K, and this was the infinite capacitor. Do we know everything, or do we need to know something else? Vt. So let's say Vt is half a volt. Given the properties of the transistor, you should be able to figure out what is the first thing you need to do? Figure out the operating point. So what is VGS 0.7 volts? Okay. What is the current? ID is 1/2 mu n Cox, which is 100 microamperes per volt square, times W by L, which is 25, times VGS minus VT whole square, so it's 0.2 the whole square, and what happens? Viola, it is 100 microamperes. Alright, so if the drain current is 100 microamperes, what is the drain potential? VDD minus IDRL. So what is that? 1.7 volts. The quiescent voltage here is 1.7. Does that make sense? What is the, so you found the operating point of the transistor, you know ID, you know VDS, you know VGS. Is the transistor operating in triode or in saturation? Saturation. Okay. So, we started off by assuming it was in saturation, calculating the drain current, and we indeed find that it is in saturation. Okay. If we found a contradiction, then we know that our assumption was wrong, and then you go and make the. We have found VGS1, we have found ID, and we know VDS1. Okay. So the operating point of the transistor is known. So what is the next job? Once you find the operating point, the next job is to find the small signal incremental equivalent circuit. And what is the small signal incremental circuit when the transistor is operating in saturation? Okay, so you need to find the GM of the transistor. And what is the GM of the transistor? Which is the easiest formula to use? Okay, here you can use anything, but I like to use 2ID by VGS minus VT. 2ID is nothing but 200 microamperes. Okay, VGS minus VT is 200 millivolts. So GM is 1 millisiemen, which means that the small signal gain GM RL is minus 10. Alright. So the incremental gain of the amplifier is 10. The next job is to find how large an input sine wave I can tolerate before the output gets distorted beyond recognition. Okay. That basically means I need to find how much the output sine wave can go down. Okay, how much the drain can go, how low the drain can go before the device gets into the triode region, and how high it can go before the transistor gets cut off. Okay, so let's find the limit for the triode region. So what is the waveform what is the absolute voltage at the gate node? VG is, yes, and what is VGS? The quiescent voltage is 0.7 volts plus whatever, some amplitude VA sine omega t, where omega is the frequency of the input. What is VD, the absolute potential at the drain? The quiescent value plus the incremental value. The quiescent value is 1.7 volts, as we have already seen, and since the incremental gain is 10, it's minus 10 VA sine omega t. And what is the condition for the device going into triode? M1 enters the triode region. This means that VD must become VG minus VT, which means that 1.7 volts minus 10 VA must become 0.7 plus VA minus VT. And what is VT? 0.5 volts. Okay, which means then that 1.5 volts divided by 11 equals VA, which implies VA is about 136 millivolts. Okay. So if the amplitude of the input sine wave exceeds 136 millivolts peak, then when the output sine wave goes low, the bottom of the sine wave will get chopped off. The next thing is to find limit for cutoff. And what is that limit? The drain current of the transistor is ID, which is 100 microamperes, plus the small signal component. And what is the small signal component? GM, which is plus GM or minus GM? Plus GM. So GM times VA sin omega t, which implies VA max, VA, the limit here is nothing but 100 microamperes divided by GM, which is 1 millisiemens, okay, which is 100 millivolts. So the limit imposed by cutoff, so if the amplitude of the input exceeds 100 millivolts, then the transistor will get cut off. In other words, the top of the output will get chopped off. VA is 100 millivolts. So what is the maximum peak amplitude permissible before the output sine wave gets clipped? It doesn't matter that the limit to reach the triode region is 136 millivolts. The moment the input sine wave amplitude exceeds 100 millivolts, the top gets chopped off, okay, and it doesn't really matter that the bottom is quite clean. You understand? So the maximum sine wave amplitude is the minimum of 136 millivolts or 100 millivolts, and that is 100 millivolts. Does that make sense? So let's go and look back on what we have done. We have figured out what we want, for what characteristics we want of a device, which so that it gives us gain. We have found that the devices people have actually made a device like that. Okay, we figured out how to bias it so that it operates in a region where you get incremental gain. Okay, and clearly, since you get incremental gain only when the transistor is biased in that particular region, it follows that if you increase the input amplitude more and more and more, eventually you will reach a stage where the transistor for some part of the signal cycle can potentially get out of that region. That is, in other words, the transistor can get out of saturation if the input amplitude is larger than a certain value. And the next question is, what is that value and how do you calculate it? And we have done that also. What is the only assumption we have made in all these calculations here? So the assumption, please note that we have merely gone along and said the drain current of the MOS transistor, for example, is the quiescent value, which is 100 microamperes, plus the incremental value, which is GM times Vs. And we seem to have forgotten one very basic fundamental thing, which is the total current being quiescent plus the incremental is alright, but the incremental value being related linearly to the input only happens when the signals are small signals. So you have to revisit. So clearly, once you assume things are linear around the operating point, these calculations are all very, very straightforward. So let's go and revisit again what is small signal. All right. So let's assume that the transistor is in saturation, and what is the current in the transistor when it's operating in saturation? 1/2 mu n Cox W by L VGS minus VT the whole square. And please note that the transistor is a 3-terminal device. So there are two input quantities of relevance. One is VGS. I mean, there are two voltages of relevance. One is VGS and the other one is VDS. And there is one current which is relevant, which is ID. In a general nonlinear device, two-terminal device, what did we figure out about small signal? What do we mean by small signal? The higher order terms in the Taylor series become negligible compared to the first order term. Okay? Alright, so the Taylor series is the value at that point plus the increment times the slope plus the increment square times the curvature and so on. Now you have a two-dimensional Taylor series. In strictly, the current ID is a function of both VGS and VDS. Alright, in general. Okay. However, for this particular device, when it is operating in saturation, the current does not depend on VDS at all, which means what is small signal as far as VDS is concerned? A function of two variables. You can expand that function around a given operating point, which is VGS comma VDS, by a two-dimensional Taylor series. Okay. In other words, you have a surface and you are approximating it around an operating point by a plane which is tangential to the surface at that point. If I increased VGS by, alright, and VDS, if I expand this as a Taylor series, I will get f of VGS comma VDS plus dou f dou I by dou VGS times VGS plus dou ID by dou VDS times VDS plus dou square ID by dou VGS square times 1/2 times VGS square by 2 plus dou square ID by dou VDS square times 1/2 small VDS the whole square plus the cross term. We will have dou square ID by dou VDS dou VGS, okay, VDS times VGS and blah blah blah. Okay. So if the function does not depend on VDS at all, then what can you say? All the Taylor series terms containing the small VDS just vanish. Alright. So this becomes 0. Okay. This becomes 0 and this becomes 0 and so on. So what is the conclusion? In saturation, the current in the drain does not depend on the drain source voltage, which means what signal qualifies as a small signal as far as VDS is concerned? Any signal qualifies as small signal provided this equation is valid, okay, which means that provided the transistor is operating in saturation, any signal qualifies as any signal, the amplitude at the drain is immaterial, it will still qualify as a small signal. Does that make sense? We saw this even in the single dimensional case, where the definition of small signal is not any absolute number, but it depends on the nature of the nonlinear. Okay? And in the single dimensional case, if the IV curve does not depend on the two-terminal device and the I versus V was like this. Okay, so this was V and this was I. Alright? What is small signal for this device? Any signal is small signal for a device like this. Do you follow? We've done this before. Okay? What I'm talking about in the MOSFET, when it's operating in saturation, is just an extension of the same thing. Any signal at the drain can be considered a small signal as far as the MOSFET is concerned when it is operating in saturation and obeys this equation. where the drain current is independent of the drain source voltage. Does it make sense? Alright. So, now the next thing is obviously to look at VGS. So, if I increase VGS by a small amount, so capital VGS is the quiescent value, small VGS is the incremental value, alright. Then this can be written as 1/2 mu n C ox W by L times VGS minus VT the whole square plus small VGS the whole square plus 2 times small VGS times capital VGS minus VT, which is ID. Please note that this, when multiplied with this term, gives ID, okay, plus this multiplied by this term gives what? What is that? Can somebody recognize this term? Mu n C ox W by L. This half gets cancelled with the 2. Mu n C ox W by L times small VGS times capital VGS minus VT. It is dou ID by dou VGS times the incremental VGS. And what is dou ID by dou capital VGS? It is the transconductance of the MOSFET, which is GM. Okay, so ID plus GM times VGS plus 1/2 mu n C ox W by L times small VGS square. This is ID plus small I, which means, so is this true for restricted values of small VGS, or is this equation true for any value of small VGS? This is true of any value of small VGS because we have not made any approximations. So we can go and cancel this guy and this guy off, which means that ID is nothing but GM VGS plus 1/2 mu n C ox W by L times capital VGSD whole square. Alright. So the small signal approximation is justified when small signal means what? Which term must be much larger than which term? Means GM VGS must be much larger than 1/2 mu n C ox W by L times VGSD whole square. Does that make sense? Since GM has got mu n and all that stuff, maybe we can get rid of all these things. So mu n C ox W by L times capital VGS minus VT times small VGS must be much greater than 1/2 mu n C ox W by L times small VGS the whole square. This is what, if this equation is satisfied for a particular value of small VGS, then we are justified in saying that that small VGS is, within quotes, small signal. Does that make sense? Mu n C ox W by L, which means that VGS much smaller than 2 times VGS minus T. Okay, and as I said, this much smaller is again now a bit subjective, alright, and we can all agree that say maybe 10% or 1% or whatever is sufficiently small. So now that is, and in our case, in our example that we did, what is VGS minus VT? VGS minus VT is 0.2 volts, and the numbers we are getting for VA. We've just closed our eyes and gone ahead and found VA, assuming ID plus GM and all this blah blah blah. Alright? And we ended up with VA of the order of 100 millivolts. Now can anybody comment on the accuracy of this small signal approximation? Is 100 small or large signal? Okay, so I can see already some people saying small, some people saying large. It's, you can see that we wanted the amplitude to be much smaller than twice VGS minus VT, which is 400 millivolts. And again, as I said, if I insisted that small signal means only 1% of, in other words, if this term has to be, say, 1% of this term, then clearly this is large signal, because right now it is 25% of the second term. Okay, all right. And if somebody says 10% is small signal, still this seems quite large. Okay, so in other words, to draw a picture, if I plot ID of the MOSFET versus VGS in saturation, what kind of diagram will I get? Parabola. What will be the value at which the parabola will cross the x-axis? VT. So below, if the VGS is less than VT, the current is 0. Beyond VT, it's a parabola like this. Okay, so you assume that this is a parabola. And this is our operating point. $100 microamperes, and this is 0.5 volts, and you assume that 0 was somewhere, way this side, so this is, let's say, 0.7 volts. Okay, so this will be about 0.3 volts. Alright, and what we have done is we have assumed that the current in the MOSFET is the quiescent value, which is 100 microamperes, plus GM times Vs. So graphically, what have we assumed? It's a straight line. The straight line will be tangential to, we assumed when we say small signal approximation. Alright? And what have we done to compute the swing limit? The voltage Vs required for the transistor to go into cutoff. Which point on this diagram represents that? What have we done? We have done, see, this is, in other words, this line, the equation of this line is ID plus GM times Vs. That's what this straight line represents. When we compute ID, when we said ID plus GM VA equal to 0, where does that stand? It's the point where the red line cuts the x-axis. So that is what we have found, assuming that the small signal model is valid. However, you can clearly see that for that amplitude, the current in the transistor is not truly, does it make sense? We have linearized about this operating point here. Then we have sat and drawn this straight line like this. And from the straight line, we have gone and surmised that the transistor will get cut off provided the amplitude is the small signal amplitude is this value. But in reality, the transistor current is not related to the applied small signal in a linear fashion. Okay, the true equation is ID is GM VGS plus 1/2 mu n C ox W by L times incremental VGS the whole square. The incremental VGS is nothing but the amplitude of the source you have put in. Does that make sense? Okay. So we are making an error when we assume that ID is equal to just GM/VGS. There is an extra term we have missed out. Alright, and this extra term, as we saw, is about 25% GM/VGS when the input is 100 millivolts. So what comment can you make regarding cutoff? We have calculated the limit to be 100 millivolts, but in reality, is the transistor truly cut off at that point or not? It is not truly cut off. There is in fact some current in the transistor, and that current is given by this value. Alright, that makes sense. So, but what can you say about the transconductance of the transistor at this point? The slope at that point is much smaller than the slope at our operating point. So you can conclude that even though the transistors, when the transistor is truly cut off, the gain is 0. GM is 0 and it's the GMRL has to be 0. However, even though the transistor is not truly cut off, the transconductance is reduced quite dramatically, and which means that the incremental gain, though not 0, would have reduced a lot from the value we calculated for small signals about our operating point. In most cases in practice, that the gain reduction is so much that the output sine wave, whether the question is now whether you predict that the output is absolutely cut off like this, or just, okay, it's nice up to here and then it kind of does this, okay. And in practice it hardly makes a difference whether there's hard clipping or it's something soft, alright. And to now estimate, so it makes, it's much easier to compute stuff assuming everything is linear around the operating point. So even though these swing limits that we have calculated from the small signal parameters are not entirely accurate, they are very, very good approximations to the true swing you'd be able to, these are absolute limits beyond which the performance is so bad to be unacceptable. Okay? So it doesn't make sense to break your head going and trying and finding the error you make, which will be small in any case, since the performance at that point, the performance of the amplifier at that point has degraded so much. Does this make sense? Okay? So which is why we will continue to use these small, truly this VA equal to 100 millivolts is no longer small signal, which means that this ID plus GM, VA and all that doesn't make sense. However, we see that the error made is small, and in order to actually compute the true value of the swing required so that the current becomes 0, it requires a lot more effort. Okay, solving nonlinear equations, Taylor series and all this. So the best, a quick and dirty way, which works very well in practice, is to just assume that the transistor is linear and compute the limits of the swing. And in practice, you would never operate the amplifier close to its swing limits. You will always back off from that. If it says 100 millivolts, you should never operate the amplifier at 100 millivolts. At 100 millivolts, there will be unacceptable amount of clipping or nonlinear distortion in the output. You would probably settle for maybe 30 or 40 millivolts. Okay, which basically means that you'll be operating somewhere around this region, where you can see that the tangent is quite a good approximation to the true I times VGS. Okay, so with that I'll stop, and I'll send out a tutorial today. I think you are now in a position to